So yes, the title of the topic is Universal Models for Optimal Power Flows in AC/DC Power Systems. And as John said, I'm an assistant professor in electrical engineering, and my research is basically power systems modeling and power systems operation and wind energy integration. Today, I'm going to focus on the modeling side of my research. So I'm going to basically give you an overview of the state of power systems, the way that we think is evolving at the moment, and is going to continue evolving in that direction. Then I'm going to briefly talk to you about operations planning and power systems in the context of power systems. What do we mean by operations planning, and where does the optimal power flow come into this whole idea of operations planning, and how network operators use optimal power flow. Then I'm going to talk about models. These are mathematical models of the network elements that we use to integrate into the optimal power flow. Then I'm going to finish my talk with a couple of case studies, one on a contrived system and one on a realistic European system, and show you how our model basically behaves and fares compared to the classical models. Okay, so the state of power systems. Well, traditionally, we all know that power systems, electricity is generated in bulk in more often fossil fuel power plants centrally located, and they are just being transmitted through interconnected web of transmission systems, transmission lines, overhead transmission lines, cables, and so on and so forth, until it reaches to us, the consumers. Now, the picture is changing, has been changing for a very, very long time with more integration of renewable energy. Now, we have centralized renewable, larger scale renewable generation, offshore wind, for example, but we do also have domestic wind, rooftop solar. These are normally distributed throughout the network across all voltage levels. So we have the transmission voltage levels, that's high voltage, then we have the distribution, that's medium voltage, and then the consumption, which is low voltage, which is the voltage that we get from our mains in our homes. And we can see renewable generation distributed across the board. On top of that, we have things like electric vehicles. Demand for electric vehicles is increasing. We do have energy storage, again, distributed mostly, but also centrally. We do also have new topologies in networks. So networks no longer are just basically an interconnected mesh of AC transmission systems. You can have AC and DC. DC, that's direct current. For example, if you have energy storage or solar PV arrays, these are DC systems, and they require some form of interface for you to be able to essentially plug them in to the current AC infrastructure. Again, electric vehicles, chargers, you have DC and AC chargers. For electrification, again, sorry about that, for electrification, again, you have multiple options. So, for example, in rural areas, you might have isolated grids, microgrids. Again, you have the option to connect those grids to the AC network. So the point here is that the typical traditional picture, which was quite simplified, you had central generation, transmission, distribution, and consumption, is completely changing and has been changing for a while. You have all these different sources of energy and demand in your system across all levels. And the job of the network operator or whoever owns the network is that they need to make sure lights still stay on, regardless of what is happening in the topology of the system. You still want to be able to drive your electric vehicle, come back and plug it in, and you expect that electric vehicle starts charging. It's unreasonable to ask the consumer to change their behavior because we cannot maintain the network. So basically, you need to figure out a way to understand and identify the sources of challenge in your system, where are the strains, where is the congestion, what are the sources of congestion, and how to remedy those challenges. And that's where the whole idea of optimal power flow comes in. Optimal power flow is a powerful analytical tool that gives the analyst or the network operator this sort of the ability to see the network, take a snapshot of the network, analyze the networks, and find out where whether or not there are any challenges that they need to address. Now, optimal power flow is the analytical tool, but the network operator and whoever owns the network also has actual hardware to address these challenges, the new challenges. So the hardware that we have is mostly electronic based, what we call power electronics. And at the heart of it is what we have here, as you can see, power converters. Now, there are a variety of different power converters and they come in different shapes and forms, but the one that gives you the most flexibility in terms of control of the power is a class of power converters which we call voltage source converters. And these converters have the ability to control your power output. So for example, if you have a battery energy storage device connected to your AC network, chances are you connect it through that voltage source converter to the AC network. And with that, you will be able to control how much power you can inject into your system. And you can do various different things as well. For example, you can use two sets of voltage source converters with a cable and create what we call a DC line, or more technically speaking, an HVDC, a high voltage DC line. We use these high voltage DC lines as interconnectors. For example, when you have offshore wind turbines, you connect them using HVDC. Or if you basically want to connect different areas, AC systems together, you can use HVDC. And the good thing about HVDC is that you are able to, again, control power output. You'll have other devices as well. You have tap changer transformers, which you can use, again, to control voltage. And you have the different types of transformers as well. You have phase shifters, for example, phase shifter transformers, again, another device that allows you to control the power output. Now, the point here is that your network has or hosts all these different elements. And all these different elements have different behavior characteristics attached to them, depends on their design, and they are actual physical devices. So they have limits imposed on them. They cannot do everything. So for example, a power converter can only operate up to a maximum power output that is designed for. That's just basically a requirement imposed on the power converter. You cannot operate a converter outside of its design boundaries, basically. So if you are a power system analyst or an operator, you want to analyze your system, you want to have a good representation of the behavior characteristics of all these different devices that are there in your network to provide those additional degrees of freedom, those additional controllabilities in your system, so that you are able to host electric vehicles, wind turbines, solar panels, and so on and so forth. So it is essential to...
¿En serio?
I think someone's got their microphone on. Perhaps they could turn it off and allow Behzad to speak.
Yeah, that would be good.
Carry on.
Okay. So it is essential that we do have a good representation of these devices in our system, in any analytical package that we want to use. Now, what is that analytical package? Now, in power systems, when we talk about operations planning or planning in general, you can have, in fact, the title of slide is more suitable to just ignore the operations. It's just planning in power systems. And you can have two sort of fairly distinct time frames in which you are after different questions, basically. So in the long-term planning, you are looking at long-term horizon, long-term timeframes, so years in advance, basically. In those planning horizons, you are trying to answer the question, okay, what happens, what sort of solutions I need to plan for years in advance, given the fact that I know that the demand will increase. Let's say in 5 years' time, I will have much more demand than I do have right now. So I need to plan for it. I need to build more capacity, maybe. I need to build more energy capacity, ask investors to invest in my energy systems, build more power plants, or I need to expand my transmission system. I need to reinforce my existing transmission system infrastructure. So that is the question of transmission expansion, generation capacity planning. So this is more or less an investment planning problem. So you are looking basically, given certain parameters, the growth in certain parameters, you're looking at how best to invest or direct your resources so that you will have everything in place by the time you reach that planning horizon. You also have short-term planning, which is more or less the topic of this talk. In the short-term planning, which spans in timeframes anything between days, multiple days, hours, to minutes, and so on and so forth. In those, you are actually looking at your current infrastructure. So you're not looking at, okay, what to build in the future. You're looking at your current resources, your infrastructure, how many power plants you have, what is the shape or topology of your transmission system, what are the tools at your disposal to be able to operate the system in such a way that is A, economical, so it costs less to all the stakeholders that use that system, including yourself, and B, remains stable for all times. Again, it's unreasonable to ask consumers to change their behavior simply because we cannot maintain our system. So the operator always needs to make sure that the system remains stable for all times, regardless of the operating conditions, and also withstand any faults, any problems. Power system is a physical system, is prone to failure. If a failure happens, the operator needs to plan the operation of the system in such a way that it can withstand those failures. And without going into the details, this area of the short-term planning has a very, very large sort of space of problems that you can address. Specifically for this talk, I'm going to focus on the optimal power flow problem, which sits somewhere between days and hours and days and minutes, typically, let's say 24 hours in advance. So you have a planning horizon of 24 hours. You can extend that as well to 48 or more than that as well. Now, the point of the optimal power flow problem is that when you solve the optimal power flow problem, you get an idea of the state of the system at any point in time. It's like taking a camera and taking a snapshot of your system. So it doesn't tell you about the dynamics of the system. So it doesn't have any sort of information about what happens to the system as it moves through time. But it gives you enough information so that you can basically know at any point in time what is the state of your system at that point in time. Now, the operators use the optimal power flow to create normally an economic schedule, a schedule of their power generators in their system that is both stable and also cost effective, typically 24 hours in advance of real time. So they do have an idea of what the demand variation is going to be in 24 hours time. They know what units are connected and committed to generate power in 24 hours time. And apologies, they know the state of the system as well. So they run optimal power flow And what the optimal power flow gives them is a snapshot of what is expected to happen in 24 hours time. It doesn't tell you the dynamics. It doesn't tell you what happens as you move through time, but it does give you distinct snapshots in advance of real time. If you are interested in the dynamics, then you need to move to a real-time operation where you actually deal with the evolution of the system state in real time and tools that you have at your disposal. So in other words, optimal power flow is basically a steady state problem. So yes, mostly operators use to generate an optimum operating regime, which is basically a schedule of all the generators and how much power they need to basically provide for the system to continue in stable operation and remains economical for all the operators. So you have some sort of function, more or less, it's basically a cost to the generators. If it's a fossil fuel plant, it's literally the cost of the fuel that you put into the generators, how much it costs. And it gives you the cost to the operator at any point in time. So 24 hours, for example, you get 24 snapshots of that cost to the operator. Mathematically, it is an optimization problem where you have an objective function and your task is to minimize that objective function. But the point here and the focus that we have as power system engineers and researchers is in these two sets of functions or equations. These are basically the limits that you impose on your optimization problem. And those limits are basically the representation of the system. So for any output from an optimal power flow to be acceptable, it needs to be feasible, meaning that the network in reality is able to actually generate that output. Otherwise, it doesn't make any sense. So you might have a very, very cost-effective power schedule from your generators, but if it's not feasible, then there is no point. So that's why optimal power flow by nature is a constraint optimization problem. Now, these two sets of equations are basically the representation of the system. These are what we call basically the power balance equations in the system. These are representative of what the system is expected to do if it is going to remain in steady state operation, okay? And they stem from basic laws of circuit theory, basically. Basically, the first set of equations tell you that at each node, if you think of the power system as just basically a circuit, a graph with nodes, at each node, you will need to have a power balance, which means that whatever power you have coming into that node, the same has to go out. Or the net power coming in and going out should be zero. That's what basically, that's in a very, very simple case, that's what the first equation represents. The second set of equations give you the physical restrictions imposed on your system. So if you have a transmission line, it has a certain finite capacity. You cannot exceed that capacity. So those are represented in the second set of equations. Now, if you have a device, a transmission line, or a controller, you need to represent properly those operational restrictions, those boundaries in these two sets of equations. And that's where the modeling comes into play. So normally what we do, we basically create model representations for each of our elements in the system. And again, the elements are modeled using what we call the admittance matrix, which is basically a matrix with some elements in it, which gives you the relationship between the input of the system to its output. So if you have a device like a power converter, you can think of it as a box. It has input and output, and it's modeled using an admittance matrix. Now, the point here is that for all the different devices that you have in your system, you need to have different models. Now, from a software perspective, if you have a sort of power system analytical software, you need to have model libraries to accommodate all of these different devices, transmission lines, generators, transformers. There are shared elements between these models, and you can sometimes use them. And we do, as you will see in a minute, we have done that in this work. And but nevertheless, you need to have distinct model libraries, especially when it comes to modeling new devices, controllers. You might have a power converter, you might have a kind of a transformer, and so on and so forth. And the point here is that if you have power flow controllers, you want to model those additional degrees of freedom, those controls that are available to you.
Okay.
Sorry, if I'm going too fast or too slow, just tell me. That are available to you, and you want to be able to model the restrictions as well, okay? And this is what we have done in this work. What we have done in this work, we have looked at the different devices and said, okay, what are the commonalities between all of these models? And what if we can just put them all in one unified model where you have everything that you need at your disposal. And all you need to do to model distinct devices is to just basically turn on or off certain degrees of freedom. And then that gives you the behavior that you expect from that certain specific device that you want. So this is what we developed. We call it the flexible universal branch model. That's just a name that we gave it to. But it is meant to represent a variety of different devices. Now, the way that it works at a simple level, again, you have a sort of an admittance matrix, which gives you the representation or relationship between input and the output in the device. And with that, you are able to create those power balances that you need. But then the point here is that you do have access to different control variables, okay? So for example, if you need to model a normal AC branch, most of the control variables are inactive. They're either 0 or just constant parameters in your system, in your formulation. But you do still have some control variables. But for example, for a voltage source converter, you have maximum level of control. In a voltage source converter, you can control everything basically between the input and the output. And for that, all of the control variables are active. Now, this table is just a representation of the actual model. You have more than 4 control variables available at your disposal, but that's just meant to give you a sort of an idea of how we develop this universal model. Now, from a software perspective, all you need is basically these individual in-model switches. So say you have a system with a variety of different devices. All you need to do is just use this one model, and you know the different settings, different control variable settings. And for those control variables that are active, they are simply an additional variable in your formulation that you need to solve, okay? And for those that are not active, they're either fixed parameters that you just carry over throughout the solution, or 0, that's it. And there is no distinction in this case between different parts of the network. So one of the challenges in modeling or solving power flows or optimal power flows in AC/DC systems is that you have distinct grids. You have a DC grid and you have an AC grid, and they are isolated from each other by the converter. So you need to solve the DC grid first, then plug in those results, do a representation of the DC grid in the AC grid, and then solve the AC grid. With this universal model, there is no distinction from AC or DC. Everything is just basically equations with some variables in them. And you are solving an optimization problem. So it's a purely optimization problem where you have an objective and some equations as your constraints. You solve them and the results are given to you, and everything basically behaves naturally. So an example is a DC grid. So in the top figure, you have a sort of a electrical circuit topology of a DC grid. You have an AC system in the left-hand side, another one in the right-hand side, and you connect them using a DC grid and these converters. Now, in the traditional modeling, you need to have three grids, three reference frames, basically. 2 for the ACs and 1 for the DC. And you need to use coupling equations to represent the effects of the DC into the AC side, okay? These coupling equations are basically the power balance equations. Basically, what that means is that whatever power that comes into the DC grid cannot exceed or the power that is going into the AC grid. They need to be balanced. Now, with our modeling paradigm, everything is just one single frame of reference. The solver doesn't make any distinction between AC or DC, and it solves everything in one frame of reference. So you don't need to solve them sequentially. You just solve them in one go, and it gives you the answers that you want in the areas that you want. Now, there's a little bit of a technicality here, because in DC, you do not have certain level of, you do not have a type of power in DC that you do have in the AC. And our model is able to make that distinction automatically. So in DC, you have everything that you expect to have in a DC grid. And in AC, you have everything that you expect to have in an AC grid, without the need to add these extra coupling equations. Those coupling equations are embedded in our model automatically. Okay. Now that's, once you have everything in place, you then formulate your problem. Again, as I said, it's an optimization problem. You have an objective, and as I said, more often than not, the objective is just basically simple cost of power generation, active power or reactive power generation, depending on the parameter of interest that you want to calculate. But then you have these array of different controls. So in the top, you have the representation of the grid in its purest form. So this is just the list of power balances in every node. But these are the additional controls that you have at your disposal, depending on the controllers that you have. So for example, this one tells you that you have control of your power in your converters. Converters are able to schedule the power. So think about this. In an interconnector, for example, you might have situations where you need to schedule power that in that interconnector to be restricted to a certain level. There might be different regulatory boundaries that the interconnector is connected to. Or there might be some sort of a mutual agreement between operators and one side of the interconnector with the other side. So for example, if something goes wrong in the other side, the other side of the interconnector can come into the rescue, increase their power output through the line, and help the other side of the grid. So these kind of flexibilities, we can have those flexibilities embedded in our problem formulation. At the same time, we make sure that all the devices are restricted within their realistic operational boundaries, transmission lines, converters, energy storage, and so on and so forth. And well, everything is feasible. So the feasible region has to be represented properly for this to work. And then what you do is just basically put this into a solver, and you solve it, and you get the results that you want. Now, the one other thing that I almost forgot to mention is that we do not need to make any approximations in this. The problem is scalable for larger systems, and at the same time remains tractable, meaning that it can give you a solution at a sort of reasonable amount of time, depending on the scale of the problem, purely by solving AC power flow equations, meaning that everything can be represented as they are. Now, moving on to the case studies, this one is just a contrived case that we just built. We basically took 2 test systems and created a what we call a multi-terminal HVDC network. We connected the systems together, and the color-coded on the highlights on the devices is basically for me to know which devices are doing what. So for example, here you have these converters that are highlighted. These are in charge of maintaining the power flow in the AC side. And these 2 converters are in charge of maintaining the voltage in the DC network. So they are able to maintain a fixed voltage in the DC network, and there are 2 distinct multi-terminal DC networks. This one is not connected to this one. So this converter maintains the voltage here, and you're able to schedule the power as you see fit using these 2 converters. So for example, if there is a problem in this side of the interconnector, you no longer are essentially connected, or you'll no longer see that problem here. You can schedule your response in such a way that does not compromise the stability of these 2 networks. This is something that you don't have in an interconnected mesh AC network. Everybody responds to any sort of event that happens. Everybody sees it. In a system like this, you don't necessarily see problems here, but you are at the same time are able to respond in a sort of a controlled manner using this converter. Or you can just basically enter a mutual agreement. You have a couple of stakeholders here, one stakeholder here. They all share this network. They might be different countries, different operators, different regions. You can enter mutual agreements or multi-party agreements to use this interconnector or this hub as best as you see fit. Schedule the power, buy and sell the power as you see fit. So these kind of networks are essential for a sort of a maximizing the resource integration, especially when you have wind turbines, wind energy generation, and so on and so forth. And with our model, we are basically able to analyze these networks for different faults, for different contingencies, what we call them, and make sure that the system remains stable and in all operating conditions. So we used our model to solve this, solve a power flow. This is just a constrained power flow. And we get good convergence results just using a laptop. And remember, we are solving a non-linear, non-convex optimization problem all the while. And with all multiple different control variables. So each of these converters have multiple control variables in them. So this one is a small system, but nevertheless, it is a hefty optimization problem, but we have good convergence. We have not sacrificed the convergence time. Now, the second case study is a real system. It's a European system with 16,578 nodes, 14,000 lines. We have 700 wind farms. Essentially, it's the representative of the continental Europe network. And we modified it with 2 HVDC links, and we basically threw every single control that we wanted to add it. So our converters were able to control voltage, power, both in the AC and DC side, depending on what we wanted. So we wanted the control settings to be reasonable, so we couldn't do just everything that we wanted to, because that wouldn't be feasible. But within the boundaries of feasibility, we try to add as much flexibility as we can. And the point of this one was to just basically test the model, see how the model behaves. And we used a 3 different solvers, optimization solvers, to solve this, solve one instant of optimal power flow for this entire system without any approximations and with those HVDC links embedded. And these are the results that we get. So we use 3 solvers, CONOPT, NITRO, and IPOPT, and these are basically different types of nonlinear solvers that you can use. We get really good results across the board. For CONOPT and NITRO, which are basically general purpose and are more tailored to solving nonlinear problems, more or less the CPU convergence time is more or less the same. We take a little bit more with the IPOPT, but nevertheless, it's within the expected values that we wanted. Now, this is important because when it comes to operational planning or basically looking at the security constraint, optimal power flow, you'll have a very, very complex problem at hand. And if you throw all these controls, you need to make sure that your convergence is still preserved. At the same time, you can scale your problem and you go up. So this is basically what we do, and we plan to publish these results. We have actually submitted one paper based on these results a few days ago. Yeah, we are very happy about the results that we are getting. The conclusion for this is that, yes, we managed to create this universal model, and that will reduce the need for having separate model libraries. So whenever you have something that you need to change in your network topology, you can just basically simply change the settings of the flexible model, the universal model, and is able to represent that. You can also use DC equations if you want. There's nothing stopping you from doing that. But we want to make sure that with the AC equations, our model actually behave well, which it shows it has been doing that. So the next immediate step is for us to test this in a sort of a potentially a larger scope problem, security constraint optimal power flow, which is another layer of complexity on the normal OPF, which we are going to do. And we have implemented this model as an open source extension in MatPower. MatPower is this package of functions that are run on MATLAB, and they're free, open source, and they're available and mostly are used by the power systems research community who are interested in these kind of problems. And we are planning to release that as an open source extension to MatPower. And we are in touch with the designer of the MatPower in that process. So we are doing that with them in conjunction. Yes, that's it. That's the end of my talk. Thank you very much. I'm happy to answer any questions that you may have. Thank you, Lynn.
Behzad, it's John here. Thank you very much indeed.
Thank you.
A delightful talk. There are a couple of questions which came up. The first was from Andy Clark, who asked, why is it unreasonable to ask a consumer to wait to charge their vehicle? Is this a new normal? And before I let you loose on that question, that was backed up by Mark Rowcroft, who said, same point, triads, etc., aim to discourage electricity flows at congested times. New use tariffs look to encourage time of use consideration in line with wholesale power price. Adding more peak capacity isn't in line with Ofgem's ambitions to limit the amount of socialized assets on the network paid for by the bill payer. I propose the consumer engagement in the ebb and flow of the network will be a significant feature of future network management. So a question and a challenge in the sense of the response from Mark there to you.
Yeah, so when I first said the talk, I thought that, okay, if I just talk about optimal power flow, it might not be that controversial. So I did through that comment because I knew that that would spark some questions. It's not unreasonable to ask to ask the consumer to change their behavior. What I am saying is that from the network operator perspective, you have some objectives that you need to adhere to regardless of what the consumer is doing. So you can have all those time of use tariffs and demand side management and all of those, and they are really fine and well. And I have done work in that area as well. But let's say if it's a football match on and your network is particularly constrained, you cannot just pick up the phone and ask people not to turn on their TV. So that is what I am saying. What I'm saying is that if I come home late at night and turn on the lights are going to turn on, and that is what I expect. And I do not, as a consumer, as a consumer that is out there, I do not need to know where that power is coming from. It's the job of the operator. So it might be a little bit controversial to say that, but nevertheless, the operator has to be able to maintain the stability of the network in all operating conditions. So we're not talking about one consumer here or even a group of consumers. We're talking about the bigger picture. So if you have the system as a whole, one consumer doesn't really come into play at all. But the system as a whole has a certain weight. So they need to be able to maintain that stability at all times, regardless of what the consumers are doing. And yes, I wasn't saying that, okay, we should abandon time of use tariffs. And because if you do that, then people like me don't have any interesting problems to solve. So yes, no, by all means, let's have dynamic tariffs. That's even more complicated. Real-time pricing and all that stuff, those are all fine and good, and we should do them. And they encourage use of alternative energy sources. One thing that I say is that, okay, this work, we just looked at physical systems, and when you deal with a physical system, everything is pretty much straightforward because it's just basically, you know what the system is going to do. But dealing with human behavior, I think there's another layer of complexity that we shouldn't really just trust the time of use tariff will solve that. I think there's another layer of complexity on top of that.
Okay.
Yeah. But I'm not a social scientist, so we're not talking now.
Do send in your questions if you have them for Behzad. I have a second one here, or maybe a third one, from Peter, and he writes, Colopt, Nitro, and iPopt total generation costs may be the same, but are the solutions the same?
Yes. What does that mean? The solution is the same.
Okay. And
I don't get that.
That was easy. Well, if Peter, you want to add anything more to that, please do.
No. Let me just say that if they are not the same, then there's a problem with your system. There's a problem with, they have to be exactly the same to the minute detail. Otherwise, there is something wrong with your system. So regardless of where you start your initialization, you have to reach the same point regardless. And none of them will guarantee a global optimum because you're dealing with a non-convex problem. So all of them are locally optimal, but they have to be locally optimal in the same point.
Right. Peter's followed up with a comment. I don't know if that's already been answered, Peter. Do they converge to the same solution or different solutions with very similar costs?
Again, exactly the same solution, exact same. They're identical, yeah.
Okay.
No, because you cannot. Yeah, sorry, I was just going to say again, repeat what I said. You cannot accept reaching similar solutions with reaching different solutions with similar costs, because that's just not, you don't have a way to compare them again. Okay. You have to have the same, yeah.
So I've got Peter says thank you very much. And Niels asks a question, could the objective function of an OPF problem be changed to minimize power losses in networks, for example, offshore wind farms?
Yes, it can. It can be. Yeah, it can be minimizing power losses. Although, so in the normal OPF, you do. Oh, sorry. Where is it? So in here, if I can bring it here, in here you do already have the losses in the network integrated. So yes, you can just change the objective function to losses in, let's say, in an offshore wind farm, and then solve and see whether or not your state variables will give you that minimum loss solution.
Behzad, I'm going to start to draw it to a close now, so I'd like to say thank you very much again for a comprehensive talk, and particularly when you start to put integrals there, a challenging one for me at the very least. So thank you very much indeed. Quick round of applause from me at least.